All right, today, section 9.2, the converse of the Pythagorean theorem. So the Pythagorean theorem itself states, if a triangle is a right triangle, then the sum of the squares of the two smaller sides, which we know are the legs, equals the square of the largest side, which we call the hypotenuse. We often refer to the Pythagorean theorem as a squared plus b squared equals c squared. Now the converse, remember the converse of a conditional statement is when we switch the if and then parts of the statement. So the converse of the Pythagorean theorem states, if the sum of the squares of two smaller sides of a triangle equals the square of the largest side, then the triangle is a right triangle. So oftentimes we use the Pythagorean theorem when we already have a right triangle. But we can also use the Pythagorean theorem to determine if certain side lengths would form a right triangle. Here's an example of that. It says, given a triangle with lengths 8, 12, and 15, determine if it is a right triangle. Well, this is easy enough. We're going to take the Pythagorean theorem and we're going to plug in these side lengths. And if the Pythagorean theorem is true, then we know that these three side lengths would form a right triangle. Now, of course, the two smaller sides have to be our two legs, and the largest side has to be the hypotenuse, right? So we need to put things in the right place. 8 squared plus 12 squared equals 15 squared, right? 8 squared is 64, 12 squared is 144, and 15 squared is 225. Now, 64 plus 144 is 208, which obviously does not equal 225. So in this case, the Pythagorean theorem does not hold true, so we have determined that these three sides do not form a right triangle. Next, I want to show you what's called Pythagorean triples, right? These are side lengths that do satisfy the Pythagorean theorem. And some of these are much more well-known than others. Like, for example, 3, 4, 5, right? If the two legs of a right triangle are 3 and 4, then the hypotenuse will always be 5. And then what you see is any multiples of these side lengths will also form right triangles. We call these Pythagorean triples because they satisfy the Pythagorean theorem, right? Some less common ones, 5, 12, 13. Those satisfy the Pythagorean theorem, and any multiples of those will also work. 7, 24, 25 is Pythagorean triple. 8, 15, and 17. Again, if we plugged in 8 for A, 15 for B, 17 for C, and we worked out the Pythagorean theorem, it would hold true. Take twice each of these sides, 16, 30, 34, they also would work. And the last thing, a little history connection. It says, some historians believe Egyptian rope stretchers used the converse of the Pythagorean theorem to help reestablish land boundaries after the yearly flooding of the Nile and to help construct the pyramids. Some ancient tombs show workers carrying ropes tied with equally spaced knots. For example, 13 equally spaced knots would divide the rope into 12 equal lengths. If one person held knots 1 and 13 together, and two others held the rope at knots 4 and 8 and stretched it tight, they could have created a 3, 4, 5 right triangle. And that's actually what we see happening in this picture. So let's label it real quick so you can see. So you can see the knots here and here. So that's 1, 2, 3 units. Here we have knots. That's 1, 2, 3, 4. So those would be the two legs. And then we have these knots here. And that creates 1, 2, 3, 4, 5. So we have a 3, 4, 5 triangle, which would make this the right angle right there.